What's up, guys? Welcome to today's show. So this is the fourth episode of the Assembly School. And before we have gone through the conditionals and computations and the basics with registers and stuff. Today we're going to discuss the topic of memory. So the memory is divided between the heap and the stack, and the line in between is usually called the break or the break line. So the stack is usually depicted on top, and the stack begins at the highest possible memory address, because all parts of memory has its unique address for the process. So the first part of the stack begins at the address of FF, 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 FF. And when we add things to the stack, those stuff get added, and the stack pointer is decremented with 4 bytes per time. And then we have the heap, which is a more dynamic memory segment where when we code C, for example, the heap is responsible for dynamic memory allocations with malloc. And it's further divided into other sections as well. But these are the two main ones. There should be like so. And when we code assembly, we manage the stack with two different operations. Either the push operation, which pushes a value to the stack. So you give, for example, EX as an argument, and it will push the value EX to the stack. And decrement the stack pointer by 4. And when we need that value, we pop it back, and then we take it from the stack and into any register. And then the stack pointer is increased by 4. So that's how the stack grows and gets smaller. Also, we have the possibility of not only popping things from the stack, but reference it directly, and I'm going to show that as well. The heap, on the other hand, when we are talking about assembly, well, we can use stuff like malloc or similar things, but usually we don't. Instead, when it comes to the heap, we use a segment of the process which is called the data segment. So basically we define where, I think I'm going to show an example instead. It's a little bit easier to understand. So let me create a new asm file. Let's call it memory.asm. And this far, when we have coded, we have basically just done stuff like this. So we set the bits and we define our entry point, and then we have our entry point. There should be an underscore there, and then we have our code here. But we can also divide it into sections. And that's what's usually done when developing real applications. So we do things like this. We say section text, and all the following stuff will be part of the text segment. And the text segment is always also called the code segment, so that is where we have our instructions for the CPU, the code we write. But we'd also want to define our data segment, where we put our variables, so to speak. So here we can put, let's say we create, first of all, we create a label. Let's say we have a label called str, and then we use the db or the d commands. So we can do db, and we can specify individual bytes that we want to save into this part of the memory. With db, we can also do a string. Don't forget the null terminator. It's not always added, and the new line is a 0A. But we can also use it for other stuff than bytes. We can, for example, use it for words. That's TW. So we can define word sized, that is 16-bit values, like this. And we can also do DD for double words, that is integer sized 32-bit values, like this. So let's create a string, hello world, with a null terminator and a 0 at the end. And we can have a multiple of these inside of this segment. We just define another label like this. And we can combine words and double words and strings, etc. And it's also okay to have a label like this without anything on the same line. So let's say we have a payload, for example. And here we have maybe a string to begin with. And then after that we have a word-sized thing. And so on and so forth. And then we can reference this in the code by this label. So what if we don't want this kind of static information? Maybe we just want to make room for a variable that we want to add content to later on in the code. Then we can basically do two things, because this data segment is read-write, so we can change it. By default, by the way, it's read-write. We can set it to read-only if we'd like. So one thing you can do is, let's say you have this payload thing, and you know that the payload will be 32 bytes. Then you can just do, well, what's usually done, you can do it like this, db, and then you fill out it manually with zeros like this. So then you have space for these things. You can also use the times, which is basically a macro of sorts. So you say 32 times I want this 0. And then the assembler, when it creates your code, it will just loop this thing 32 times and put it here. So that's possible. But when we use zeros like this. We usually put it in our own section, which is called the BSS section. So BSS is for uninitialized data, where we want to save things during runtime, basically. And then we use not the D types of things. Let's say we remove this payload here and we want to do the same thing in the BSS section. What we do is we define the label as usual, but now we can use the reserve instruction instead. So we can do resb 32, for example. This means that we are gonna reserve 32 bytes of memory, which will be filled with zeros usually. And then we can reference this payload during runtime. And this doesn't take up as much overhead as the data segment version does. So this is the preferred option if you have the possibility. In some occasions it's not possible, depending on what you're coding. But if you have access to a BSS section, you should do it like this. And then you can just use these things. For example, I think we have done this before. If we want to print this hello world string, we move into EX, the write system call. Into EBX we put the, let's see, standard in, out, error. A 1 for the standard out. And in ECX we put the string. So we put the label here. And that will reference this string right here. And then we need the size as well. A neat little trick is we can define it like this. So we create a label for size. And then we can use a special kind of macro thing. So we can do, we define this as a byte, a dB. No, let's make it a dd, because it wants an integer. So, and then we can do $$ minus $, which basically takes the difference between the memory address str and size, and size minus str is equal to the size of this thing. So then we can just move the contents of size. So what's the difference here? When we reference the str, we want the memory address. So basically the pointer to this string, the thing that str is referencing. But when we are referencing size here, we want the actual value, which is here. And we use these square brackets to signal that we do not want the address, we want what's at the address. And then we can just execute the 0x80 system call, and we can clean up by putting a 1 in EX, a 0 in EBX, and executing the exit. And if I have thought about this correctly, it should be able to compile. Did. And let's run it. Not a lot happened. But it did not crash though. No, this is not right. Something must be wrong with the makefile because, as you can see, it took the wrong code. So let's check this makefile. Alright, so what does this do? We do a wildcard match on ASM and put it into sources. We create objects by putting a .o to that and binaries without the extension. When we run all, we go through, let's see. We run our assembler with our flags and we specify this. Let's watch the make output and see what it does. So we do nasm.o elf memory.asm, but we take the computations when we link. That's not right. So let's see if we can change this maybe to a symbol like this. Make clean, and we make. No, now it tries to do them all. So we want to go through each of the binaries. Maybe we should not put a So binaries contains different things. And as we can see, we do the different things. But the source is the problem. And the source are these objects. Maybe we should set the source as Is it possible to do? Let's see. What we want to do is we want to take the name of the binary .o as the source, and we'll put back our old arrow. Is this possible? Let's see. No. So how do we just take the right one? And I suppose we cannot do this either. No, we cannot. So what if we do something like this? We give the objects as the source, but we change this like so. Will that work? Okay, that worked. But it's a bit of a hack. I think there is a better way to do this, but let's don't worry about it any longer. Let's see where my window went. Here it is. So let's run this memory, and it's still something wrong. Okay, so now it executes the write, but it seems a little bit weird. Maybe I reversed these, because as we can see, I gave it the wrong size, so it tries to read from the entire memory basically. So what if it's dollar minus dollar dollar? I always get those wrong. Yeah, there we have it. And if we do an trace on this, we see that we execute the write system call to the standard output file descriptor with this thing, and we give 13 as the size. So we basically try to output the 0 byte as well. We should probably have done minus this, minus 1 in this case, since we specified the 0. So it's also possible to do stuff like that, where you basically do arithmetics on the assembler level, but this will be resolved at compile time. And we can also do a little bit of stacks things. Let's say, for example, that that we don't have, let me think. Let's say we use the stack and we push. First of all, we move the string into some register. Let's do EX, for example. So into EX we move the string, or the address of the string, and then we push EX. So now it's on the stack. So how do we access it? Well, one way is we can pop this into a register, ECX for example. And so we can comment this out. So now we pop it back into this register. And let's also clean EX. It's not really necessary, but I like to do it that way. and we run this, and we should get the same result. We do. But we can also access it from the stack without popping it. And as I mentioned, the stack pointer is always pointing towards the top of the stack, basically where the next push operation will be. So what we can do is, before we push this thing, we save the value of the current stack pointer into ESI, for example, a register we're not using yet. So into ESI, let's do a move instruction. Into ESI, we put the current value of the stack pointer, ESP. Then we push this address to the stack, and we do not pop it, but instead we will move into ECX the value of ESI. And watch the brackets here. So ESI will contain the address on the stack. So if we were to visualize this, we have the highest possible address, FF. And then there we put the address to string. And this is what will be copied into our ESI register. And then we push to the stack. So this is the stack. Then we move into ECX, not ESI, because that would be this FFFF address. And we need to have the real address of this. But at this location, we do have this address. So by using these brackets, we take the value at this position, which is the address to str, and we put it into ECX. And if I have thought about this correctly, we should be able to line 14. Oh, I forgot to remove the comment. Let's run again, and let's see if we get the right result. No, we did not. Interesting. Let's see. We try to write at the position 1. Maybe we should reverse this. So first we push, then we move into SI. And now it works. So I need to correct myself. The stack pointer is not pointing towards the next thing to be pushed onto the stack. It is actually pointing towards the last value that we pushed to the stack. So if we need to visualize this, we have this address FF, and we have the address to str. And then after our push operation, the stack pointer will be equal to FB, right? Because it's C, D, E, F, right? So B. And at this position we don't have anything, so that's why we got this weird error. And we can also watch this code inside of objdump. And here we see a little bit more explicitly. So we move into EX some address, and if we check the memory, this is 4A000, 4A000. So this contains our str, and it tries to translate this to assembly instructions, but this is the string. And then we push EX and we do all this stuff. And when we look at the assembly output, we can write it like this inside of NASM as well. So we move into ECX, double word, pointer, so 32 bits, and what's at the ESI values location. I wrote it like this, but as I mentioned, we can also say D-word pointer, or maybe it's more correct to do like this, D-word pointer. But that's basically only in the assembly, disassembly, we see that stuff. And this is a little bit interesting as well, because at this point we move into EDX, the value of size. So if we look at this, we move into EDX, the D-word pointer, DS, and this. So DS in this case holds the data segment. So if we look at the exact address, it ends with 0D, and 0D contains 0C. And if we check what 0C is, we can see that it's 12. So everything works as intended. Yeah, well, now I think you do have all the bits and pieces to be able to use data inside of your ASM projects. Thank you for watching, and thanks for today.